get the recording going before I forget. I will be posting the recording on the Innovate Bio website, so you'll be able to find that on Monday. There's a link, you'll see a link on the front page, but you can also just use innovatebio.org/presentations and you'll get there too, which is pretty quick. At the end of the webinar and probably somewhere in the middle, I will be posting a link to a survey because we always like to hear your feedback, make sure we're getting the topics that you'd like to hear and learn more about. And well, there's no question today, we have very entertaining speakers, so I know you're going to enjoy this.
Okay.
All right. So our wonderful presenters today are Lisa Seidman and Rodney Null. Lisa really almost needs no introduction. She's been teaching biotech for a long time, and I understand Rodney teaches math. Yep. I've heard rumors to that effect anyway. Yeah. And you may know Lisa also has a book about laboratory calculations that you can find links to on the Innovate Bio website, and I'll put a link in the chat at some point. And also, she's also famous for writing, I guess, the Bible of biotechnology education as well.
Not quite the Bible, but a big book. Yeah.
All right. Take it away, Lisa.
Okay, thanks, Andy. So we think that it's really important to collaborate with biotech people. That's me and Rodney, who is our math person. And I'll just say, Sandy did a nice introduction. And I'll just say that I'm now semi-retired, but still working on writing books and still teaching. And my students actually are in class even as we speak with somebody else. And anyway, so Rodney, why don't you say a little bit about who you are?
Sure. Hi, everybody. I'm Rodney Null. You probably don't know me as well as you know Lisa. I will admit I have done some mathematics in the past. I sort of made a living at it for a little over 3 decades, and my experience ranges from middle school all the way up to university, but the lion's share of my career has been at the 2-year level. I am professor emeritus right now from Rhodes State College, and which is in Lima, Ohio. And Lima is an acronym for Lost in Middle America, by the way. And I'm a pleasure to be with you today. I appreciate Lisa inviting me. Us math folks don't always get invited out to play with the other kids. So I hope we can have a good get together today.
Great. Okay. So we're going to start with a little question, a little math question while people are still joining the webinar. We're going to have a couple minutes. Rodney, this is your problem. Why don't you introduce
this is my fault. I mean, my problem. This is something I use as part of an activity for students in a number of my classes. And one of the issues I had was folks coming to this discussion with just enough knowledge to be dangerous, basically. So I try to take them out of their comfort zone here, and which is I'm hoping what I can do with you. So the scenarios involve farmers getting together to swap produce here. So prior to the swap, there's an establishment of equivalency in value, understand, not weight or something like that, but in value amongst the different crops that they are growing at different times, so that there's not too much dickering and bartering and stuff like that and disagreement about best deals and things. So given these equivalencies in value, if we have a farm, Veggie Best here, that's got 450 zucchinis that they need to trade for tomatoes right now, we'd like to know how many tomatoes they ought to be getting from their trading partners. So we'd like to give you folks a wee bit of time there to contemplate that and think about how you might solve it and actually see if you can come up with an answer, and we will want to know how you did that in a little while. So we're just going to take a little time here for you to do that.
Yeah, we will come back to it later, and if you don't get enough time, don't worry. We, just try it, see if you can, in the time we have. Okay, Rodney, you're kind of timing this a little
bit. Inspirational music. I don't know if you can all hear them. If I can pause it, stop. There.
Okay.
You can work on that in the background as we're talking about some other things. We don't want to dawdle too long here for this.
Right. Okay, but if you've started or if you just looked at this problem, that's great. We will come back to it and we'll ask a question about it. If you just have even taken a stab at it, that's perfect. Okay, so we'll move ahead and we'll turn away from vegetables and we'll start talking about some other things, more biotechy. So we're talking about math as a problem. So first of all, what is that problem? And let's start out with this. Numerical proficiency is a requirement for success in STEM, and I don't think too many people are going to disagree. There's probably some jobs in STEM where you don't need to use numbers very often, but mostly, most of the time, we do some kind of calculations in STEM careers. Now, I wrote, many people struggle with math, and Rodney wrote,
all people struggle with math. The perception that folks have of you either know how to do it or you don't, or you're good in math and I'm not and stuff is something I'm always battling with. There's plenty of math that mathematicians struggle with. I know people that have their PhD in math that have trouble balancing their checkbook. Okay. Maybe that's a math issue or not, but okay. If you stick with math long enough, you'll find difficulties with it.
And so what people often say is their students can't do math. And I have plenty of friends, adults, who are not in STEM fields who say, well, I never went into STEM because I can't do math. So there's this idea about not being able to do math. And it is true that people often have difficulty performing the math required on their job. And one of the reasons I kind of got interested in this whole math field was not because I really wanted to get into math, because I have to tell you, I didn't really like math very much, but it's because my students were struggling with it. And I had a student who worked really hard in an internship at one point and was told by his internship supervisor at the end of the internship that he was not hireable at that company because he made too many mistakes on his calculations and he couldn't do math. And of course, he was very upset. So this is the sort of thing that I started dealing with when I started teaching, and I started teaching a long, long time ago in biotech in 1987. So it's a long time ago. And here's a really big issue for us, which is that math becomes this barrier that keeps qualified people out of our field. And I don't know, our program for sure needs more people. We desperately need more students, and our employers really like our students, would like to hire more of them if we only had more of them. So we do not want math to be a barrier keeping people out of our field. So one of the things that I think is really important is that we can't just say you have to be able to do math to be in STEM. We really need to look at what do we mean by that. And there have been studies that try to drill down into this to say, okay, we know that you need to do some kind of calculations, but what exactly are we talking about here? I'm going to just give you the summary of some studies. There's a slide at the end with some references to various studies, and this will be posted so you'll be able to see those references and you can look at them later. So various studies have come up with what's required for biotech, and all the studies come up with basically the same things. What do we mean when we say math is required in biotech? Well, we mean mathematical operations, addition, subtraction, multiplication, division, proportional reasoning, some bit of logarithms, some descriptive statistics, graphing, data manipulation, simple equations. Basically, things that students learn in like 8th grade math, 9th grade math, or middle school, things that are taught very early, and not things like calculus, or not even particularly advanced statistics in most jobs. Now, that's not to say that you never need higher level math in any STEM job. Obviously, researchers might need more advanced statistics. I've seen calculus in population biology problems. But in general, these are the things that our students, say in a molecular biology lab or in the places our students go, these are the kind of things they need to do. And here's the really big point, and I think this is a really key point for us, which is that in our experience, our average students, our associate degree entering students, can do the math manipulations required. There are some gaps like logarithms. Some of them have never seen anything in statistics, but they generally can get through what we would call, say, 8th or 9th grade algebra, at least solving an equation with one unknown. The problem for our students isn't that they can't do math. And so if we start out there, then we have to say, well, okay, if that's not the problem, then what is the problem? And I would say the problem is that they can't find the math in an applied situation. So you've got math on the job, it's all word problems. In the vocabulary, the context is unfamiliar. Like all of a sudden they're talking about picomoles. Well, what in the world is picomole? And I think Rodney's got a more sophisticated way to talk about this. So Rodney, we'll let you here.
When Lisa and I had initial discussions about this, I thought about this for a little while, and I guess I started ranting. And so I at least made a partial list of some of the problems that I think we have with the way math's taught and the curriculum and stuff that's often used that produce the types of situations that Lisa refers to up here. If you look at standard textbooks, traditional types of scenarios, they're lacking a number of the attributes that are required in that job setting there. So, relevant skills such as estimation, reasonableness of answer, picking the units that are appropriate. Sometimes units aren't even included in those textbook
A
problems.
lot of times. Mhm.
Experimental design, figuring out how to set something up, what variables to control and stuff like that to explore a problem that you're working with. Actually measuring and collecting their own data is rarely given there. If they are based on data, they're given the data sets often, and they're very contrived and already organized or cleaned up and stuff. Identifying necessary and sufficient information, eliminating irrelevant and extraneous stuff. I give students all kinds of stuff that they have to sort through to figure out what's relevant. I tell them, my zodiac sign, what year my first car was, and stuff like that. And then when it comes to actually measuring things and stuff, dealing with natural variations, I have, 10 different groups of students measure the length of this classroom and they get 10 different answers, and they have trouble dealing with that. And another thing that because this list is almost infinite, figuring out the appropriate math tools in an appropriate situation is a challenge in the real world. But in the math world, you just have to look at the title of the chapter. Hey, it must be exponential functions because that's this chapter we're in.
Right.
Figuring
Right.
out the math in the setting is one of the tools there.
Yep, great. Okay, so Rodney did a great job summarizing the problems with why, I guess, our students are having trouble with this. And I wanted to put in a concrete example from our discipline where students might struggle to find the math, and it requires some underlying knowledge and vocabulary. So here's the problem. So vectors are DNA molecules that carry a DNA segment of interest into a foreign cell. Suppose you buy a vial of the plasmid vector PBR 322, which is 4,361 base pairs in length. Manufacturer tells you the vial contains 10 micrograms of vector. Your following procedure calls for 1 picomole of vector, so you want to convert 10 micrograms to picomoles. How many picomoles do you have? You're given a conversion factor, which is a base pair's molecular weight of 660 grams per mole. So basically, this is a unit conversion problem. And unit conversion problems are solved with multiplication and division or simple algebra. I mean, that's basically what this is. But it looks a little bit challenging. And Rodney, you had a response to this.
Well, okay, amongst the 43 folks we have here as participants right now, 42 of you are going, oh, it's the old vector DNA molecule problem or something like that. Me, the math person, is looking at this like vectors. Okay, that's what we did in physics class. That's dealing with polar coordinates. That's magnitude and direction. That's not what you're talking about, right? Yeah. I look at this BP. Is that blood pressure we're talking about? It seems pretty high for blood pressure. And as students are reading a problem like this, you're guaranteed to get 322 into the calculation somehow because it's a number in the freaking problem. And a picomole, that's a really small mammal that digs in my backyard. The confusion level and asking the average math person to deal with this context cold turkey is really not realistic, I don't think so.
And that does get to an issue which we're not going to really address right now, but some of the issue is about who should be teaching this. And we'll sort of allude to this a couple of times. And one of the things Rodney has told me is that this would be really tough for him to teach a course that was like this and filled with these kind of problems. Okay, so there are some solutions, and that sort of does get to this this issue. And I think, we're going to talk a little bit this at the beginning, helping students find strategies that are directly applicable to the problems that they're going to encounter. So just because students learned how to multiply in grade school, and they can multiply, especially if they use their calculators, we can't assume that they know when to multiply in a contextual problem. And that's the really key issue. And I do think we can help students to find strategies to do this and to know when to multiply. And I put a little asterisk here to remind me to tell you that it turns out that when I first started getting into this math issue, I thought I was just going to be helping my students be more successful in my course. Little did I realize that I was leaping into this huge controversial area that is filled with passionate beliefs that completely are contradictory to one another. It's a minefield, and there's all sorts of politics at the national level, big money involved in this whole discussion. So one of the first places where I discovered this is right here, because I started setting up a course to help my students be successful. It's a little 1-credit course. We eventually incorporated that into the program. And we went to a conference that Rodney was at many years ago. And I think Sandy and Linnea were at this conference too, where we presented information about our little course. And when I came home from this conference, one of my friends, Judy, who was a math teacher, said to me, well, it's very nice that you went to this conference and you got recognition for your little course. That's great. But I think what you're doing is wrong. And that is her direct quote. You are wrong. And it's like, whoa, how could I be doing something wrong? I'm just trying to help my students. She said, well, if I do my job as a math teacher properly, then students should be able to leave my math course and apply what I have taught them wherever they go, whether they become biotechnologists or firefighters or nurses or doctors or scientists, they should be able to do the math. And I've thought about that for years, and it sounds really good, and it should be true. But the reality is that I can't do it. I can't apply things that I learned in a math course intuitively to problems in the real world, and my students mostly can't. And most of the people, I do know some people who can, and most of those people are math teachers. This is the classic issue of transferability. So, Rodney, do you want to leap in on this at all?
Boy, we need another hour for me to really do justice to that. I think transference is clearly problematic, and it's phenomenal how difficult it is for many students to apply math even in slightly different circumstances. I mean, we sort of joke, students know what 3 apples plus 2 apples is, but they can't do 3 oranges plus 2 oranges. It is almost that serious sometimes. And it's a challenge for us when we're sitting in a math class where I've got, a potential biotech student. It's a general ed course. They take it well before their programmatic courses. So I've got a potential biotech student sitting beside a potential engineering tech student sitting beside a business major or something like that, and coming up with a context that's relevant to where they're going and meaningful and engaging to all those different audiences and stuff. So, even though I can give them basic math sometimes and try to do it in context and stuff, when you get to that programmatic course where the context is so much richer, so much more challenging and stuff, their transference, their ability to apply math in those settings is compromised often. So I applaud Lisa. She's addressing the problem at its roots here with what she's doing.
Okay, and that is one of the reasons I love to work with Rodney, because he has never told me that what I'm doing is wrong. He has told
wait
me,
a minute.
No, you have told me some of my calculations are wrong, or my answers are wrong. But my approach is, you never told me that teaching my students directly in our courses.
Yep.
I, as a biotech teacher, teaching them how to do these calculations, I think is right. And then the second thing, we're going to try to have some time for Rodney to talk about some long-term systemic solutions, because really, just us teaching students how to do things in our little classes, it's great and it's really helpful to our students. But I don't think on a more global issue, it doesn't really solve the problems systemically. So we want to get some time for that later. So there's good news and bad news about this. And the good news is that we did incorporate this many years ago, like in 1990 or something. We started with this little 1-credit course and started teaching our students how to do the math in really common biotech situations. And it's really good news because we got to be more confident that they could do the math required. I wasn't so sure for a while, and they became more confident. And so I wish I could had a study that really researches the effects of this course in some formal way, and I don't have that. But what I do have is student evaluations and student comments. And I know that anecdotally, they do like the course. They do feel like they become more confident. Just taking the students out of the lab, giving them a little bit of time in the classroom to memorize metric prefixes, to practice unit conversions. This is really helpful for them when they get to the lab to feel more confident that they can do it. And the bad news.
Just one additional thing to throw in there. I think one of the nice things you just described, Lisa, is that you're not just helping them with those metric prefixes and things, but they're using it consistently throughout. Right. One of the issues that comes up in math is, a topic like that may be addressed, but it's addressed in a very confined, 2-3 day period, and it's never used again throughout the rest of the class. So it's not reinforced. They don't build the confidence and the functionality with that topic.
Right. So we pick topics which we know they're going to use over and over, and they are in their parallel courses. So the bad news is it takes time. When we develop this course, and I know that not everybody can do this, but we wound up making a 1-credit course and then dropping 1 credit out of another course. So we actually had to take subject matter away from someplace else. And it was I think it was worth it. I think it really helped our students, but we were sad to lose the content in the other course. I think that's just how it is. And the other good news is that it's just a 1 credit course, but we found, and I was a little worried that 1 credit wouldn't actually even be enough. But by working through a few of these really key introductory topics, at the same time as they're taking our regular lab classes, so they're doing this in parallel, it really did make a difference. And we didn't have to get all that far. As I say, a couple key topics makes a lot of difference. So we're going to talk about one of these topics in more detail. It happens to be unit conversions. You might have already had a clue that that was the topic. And we're going to talk about it a little bit to sort of make this more concrete. So we're going to talk about unit conversions. And one of the reasons to do unit conversions is also because the needed math project, which is one of the projects that's represented here that Rodney and I are working on, we represent. The needed math group did a virtual site visit to a company called Neogen, which is a biotech kind of testing company. And when we were in that company, they were asked, what kind of math do people do at that company? And the supervisor wound up spending, I don't know, like 5 minutes on what he called a dimensional analysis problem. And it was something about nanograms per mil and 10 parts per million. So either you had to convert 10 parts per million to nanograms per mil or nanograms per mil to 10 parts per million. It wasn't totally clear. But the point is that this was a unit conversion problem. And he used a dimensional analysis strategy to solve it. And he thought this was a really important math thing that they did at their company. So we're going to talk about unit convergence, partly because we saw it at Neogen. Partly because it's one of the first places where students run into trouble. And I will also comment, it was one of the first places I still remember running into trouble many years ago when I did freshman chemistry. I really thought I was going to flunk freshman chemistry because I could not do the unit conversions. And that was like in the first week of class. I couldn't understand what the TA was telling us. I was completely flummoxed by these conversions, even though I was taking calculus at the time and it was doing me absolutely no good. And I eventually did, luckily I am here, I did not flunk chemistry. I did figure it out eventually using my own way. And so I do think it is a real obstacle. I don't think I'm the only student who ever ran into trouble with unit conversions. The other reason we're going to talk about unit conversions is because it's so interesting. It's a really hot button. I said that math is a landmine, you know, it's filled with landmines. This is one of those topics. So on to unit conversions. The basic math is multiplication and division. And as I said, it is a landmine. So my approach. So I'm going to start and I'm going to talk about what I eventually taught myself to do and how I approached teaching this initially to students. Not the only thing I do with them, but one of the things I started doing in our little class that we have. So I start out with what I call the chocolate cake problem. And I find it's completely intuitive for every student. So I tell them, I'm going to bake a cake. That cake requires 10 ounces of chocolate. But let's suppose I want to bake 2 cakes. How many ounces of chocolate do I need? They all know I need 20 ounces. This is the chocolate cake problem. And I do a bunch of these with the students. We can just do them, you know, verbally. You know, if you want to buy lattes for all your friends, 1 latte costs $4. How much is it going to cost for your 10 friends? Whatever. We could do a bunch of these where they know the answer. And every student knows the answer. So it's not a problem because they know what the answer is. They know how to solve that kind of problem. It's intuitive. And then we can talk about ratios and proportions. We can make it a little bit more mathy. So we can say 1 cake requires 10 ounces of chocolate. That's ratio. We can set this up so that it looks like, oh, an equation. So now we have this equation that looks like algebra, and most of my students are pretty good with this. They can get this far, they can cross multiply and divide, and they can come up with that the unknown is 20 ounces. You need 20 ounces of chocolate for 2 cakes. And I usually take time. This is where some of the time comes in. I'll do a bunch of these with the students where they already know the answer. And then they can, you know, practice setting this up as an algebraic equation. We can eventually go to ones that are a little bit more complicated, feet to centimeters, where the 2 conversion factors are going to require 2 proportion problems to give an answer. Here it is. First, you convert feet to inches, and then you convert inches to centimeters using 2 proportion problems. So this would be the way I would begin with students. And again, as I say, it takes time, but usually most of the students are okay with this and they feel pretty comfortable, you know, after a while. So, okay, their confidence is up. And then we're going to have Rodney show his way. Oh, but I do want to say this. Okay, go ahead.
No,
I want to get rid of dimensional
first.
analysis. No, okay. I want to get rid of dimensional analysis as their term.
Okay, all right. Let me sneak into.
Okay.
I think a key thing in Lisa's description of her chemistry experience and her chocolate cake and stuff like that, that occurred how many years ago, Lisa?
Well, which, the chocolate cake or the chemistry? The chemistry was like,
because I don't know that they're independent of each other. I think you struggled with a concept and you came up with a paradigm, a thought process, a technique, a method that you understood, you developed it, and you worked it into that situation, that challenge that you were having in chemistry land, and nurtured it over a period of time and built confidence with it, and you own it now, I guess is the way I would say it.
That's right. And I do teach it. So we do want to have our students develop their own, and that is a point we're going to get to later, because that's my method. Obviously not Rodney's, as you will see.
Well,
but we do want our students to develop these kind of techniques. And I really do think it's a good idea to start with things that are intuitive and easy for students. So that's why I like my method.
Sure.
Dimensional analysis, which Rodney will talk about. I want to get rid of the term because it's not informative and it's intimidating. And it sounds like you're measuring a box, like it's, I don't know, 12 feet by whatever it is. Anyway, so my favorite chemistry teacher calls this the unit cancellation method. I believe, Rodney, you called it factor labeling, but
it goes by many names.
By many names. Okay, so Rodney, you are on now.
Sure. Okay, so the 3 feet, turn that into how many centimeters is one of the problems that Lisa was addressing there. So I always start out with where am I at and where do I want to end up? Well, we started out with 3 feet, and I wanted to end up with however many centimeters was the equivalent of that. So I set it up as 3 feet, which is equal to 3 feet over 1. And then I'm looking for equivalencies or conversion factors that I can use to basically make feet go away and centimeters ultimately end up with here. So each of my little set of parentheses there has a conversion factor that I was privy to. I believe those are the same ones that Lisa had. And I describe those fractions in there as fancy ones. If the numerator of the fraction and the denominator fraction are equivalent, the value of the fraction is 1. And multiplying by 1 doesn't change the value. It may change the form, but it doesn't change the value of what you started with. So if it's 3 feet at the beginning, the value that I end up with at the end will be the equivalent of 3 feet, even though it may be in a different form. So I think most of you are familiar with this technique. And I had to use 2 fancy ones to get from where I was to where I wanted to be. I think I'll be quiet there. I can talk more about that.
Okay.
Done.
Right. So, and I actually, in my class, we do practice both methods. So we do unit cancellation too, but I start with proportions. Okay, so let's return to vegetables. Okay, we're going to go back to vegetables. This was the problem. I know a few people may have come in after we tried to work on this. That's okay. At the very beginning of the talk, we just asked people to quickly try to solve this. If Veggie Best Farms has 450 zucchinis, they want to trade for tomatoes. How many tomatoes will they get? And very quick. Yeah.
I was delighted to see in the chat window, not too long after we put this initial problem up, folks posting some answers. And I was also delighted to see that they didn't try to deal with fractional tomatoes and stuff.
Right.
I'm impressed, gang.
Right. Yep. And I'm just really quickly going to go through this. We have Rodney's approach up at the top, which you will see is one beautiful, elegant, long equation where he cancels out all the things and winds up with roughly 171 tomatoes. Lisa's approach using proportions does require 2 steps. Therefore, it's not quite as beautiful, I admit, but I got the right answer. He told me I'm right. So at this point, we're going to do a poll, and Cassandra is going to do this for us. So we're going to ask people to tell us whether they were using Lisa's proportions approach or whether they were using Rodney's approach.
Lisa and I have a little side bet on this, so no pressure.
Yeah.
There's money involved.
Pressure there, yeah. Right. Okay, and the results are pouring in. And if you didn't quite finish it, that's okay. If you just, even want to vote anyway. Are we done? Have I won? Whoa. Whoa. Okay. Cassandra, I think we can end the poll.
Okay.
And I won by a small amount.
And we only have one other. Oh my gosh.
Okay. This is because we're working with a lot of biologists.
You want her to share the results?
Yeah, so Cassandra, can you share the results? I'm not sure what everybody's seeing. I know what I'm seeing.
I'm curious how many of these people were in that same chemistry class as you.
I don't know, they have to be pretty old. Okay, Cassandra, now can we make that screen, or should I just make it go away?
I can stop sharing, yes.
Okay, so we had 53% for Lisa and 44% for Rodney and one other, right? Okay, great. I'm going to make that go away.
Bob is not in my corner in the chat. He says end the poll while Lisa is winning.
Great. Okay, let's see, where's the next? Why am I? Oh, there. And we did want to leave a space here. Would the one person who said other like to share their logic? Unmute themselves. Would that person like to say something?
No, that this is Uwe. It was just a mix of both approaches, and that was not a part of the solution. So
great, and thank you. You know, I actually, that's great. I actually do. I noticed myself, you know, that I'm a little bit more experienced. I do mix both approaches also sometimes when I'm solving problems. So that's great. So we have one that's mixed.
I see Laura makes a comment about it. In math class, students are told not to cancel for numbers. They find one or something like that. How do you explain that for units? Well, so I would be curious about the not to cancel comment. I mentioned to Lisa, if you ask students to put a fraction like 16/64 into lowest terms, often they'll correctly give you the answer. It's in lowest terms, it's 1/4. And you ask them how they got that fraction in lowest terms, 16/64. Some will say they scratched out the sixes, which works. Well, I mean, it gives you the answer, but the reasoning sucks, I guess. So, and it doesn't work all the time. So figuring out what that cancellation constitutes would be an issue. I actually don't teach the activity that I showed you for the farm co-op thing. I ask students to go figure it out themselves. And I get some of the best peer-to-peer teaching and stuff, something we may talk about a little bit later. One argument I heard between students and groups was, stop looking at the numbers. The words are what you have to pay attention to set this up. Don't do any arithmetic until you get the words right. And so I thought that was a great explanation of how they ought to organize their thinking and stuff when it comes to doing an application like this.
Great. So we just had our little bit of a discussion, and I think we'll just go to the next point, which was what works best, what's the right way? And well, half of us did it one way and half of us did the other. Rodney and I agreed on this answer. What's the best way? And we both agreed, and I think, Rodney, you put in those exclamation points.
Absolutely.
We both agree that the best way is the way that works for you. Now, I will tell you that this is one of those landmines, because I'll give you one example, which is my students had a chemistry teacher a while back who gave them a bunch of unit conversion problems on tests. And if they used proportions to solve the problem, he gave them 0 credit for it, none. They had to set it up using dimensional analysis, or they did not get credit for the problem. And we have also, Rodney and I have had a rather heated discussion with another person who also believes that the right way to do it is dimensional analysis, and we should just teach that. So this is definitely a place where people have disagreements.
It's interesting. I've given my students the choice also, one of having a sheet of conversion factors and another having a deck of cards. And on the cards, basically, you had those fancy ones. One side would have the 12 inches over 1 foot. The other side would have the 1 foot over 12 inches. And they could lay the cards out to set up the problem. And they often like the cards because of that physical manipulative, I think, as opposed to looking at a reference sheet. So different things.
But I do think it's really interesting. We did our little poll and we got all close to 50-50. Not quite. I did win, Rodney, but
I noticed.
but we got very close to 50-50. So I think that really makes the point well, that as teachers, for us to demand that everybody do these kind of math things in the same way is probably not the best strategy. And the other thing I'll also point out is that I gave this, I asked my colleague Jeanette Mowry to solve one of these problems. Oh, 1 second, Sandy, and I'll get to you. And she used both methods actually, because she made a mistake with her dimensional analysis and then checked herself with proportions. And her point is that being able to use more than one way is really important. So Sandy, we have your hand up. You're muted though. Sandy, you're muted.
Thanks.
Yeah,
There are a couple of comments in the chat that I thought you'd like to hear.
Okay.
Marnie Landry says she thinks she teaches it your way because she avoids referring to the math they used in other classes because they shut down.
Okay. Ooh, that's really interesting. Wow.
Yeah, and she
Yeah.
liked Rodney talking about noticing that students, if they say pay attention to the words,
Yeah.
that's
Yeah,
a
that's
good thing.
good.
And then
That-
Beatrice says that there are different ways to resolve the problems, but getting the right answer.
It's really
There's
important.
different
Yeah.
schools in other countries. You might
Yeah.
see things. And Jonathan Margulis is wondering about getting his hands on one of those decks.
Well, Rodney.
Jonathan, I had somebody very, very good at that help me make those. So you'll have contact information on me later. Let me know. And then somebody talked about doing them both ways for error checking. Yes, but you got to be a little careful. Sometimes students really want to gravitate to one way that they feel very, very comfortable doing, as opposed to having 17 different ways, I'm exaggerating a little bit, that they have to choose from. So.
Yeah. Right. And that's fine too, but I think as people become more sophisticated, having more than one way is great.
And Uwe
Well-
has a comment too that's good, that if you did that zucchini problem backward, you could see like how many zucchinis you'd get for 171 tomatoes.
You could. That's another strategy for checking yourself.
And because
Excellent.
of the rounding, I wonder if it'll always come out exactly the same.
Okay, now you're talking math.
Hmm.
So let me briefly come in. That's not another way. I don't care about I would demand that they would do, before they submit an answer, that they do like how many zucchinis do I get for the answer that I found. And Rodney, yes, the rounding doesn't work very well, but it doesn't matter. I mean, there's more stuff to discuss that way, but on the same track, they get a little bit used already to quality control and that kind of thing.
Yes.
Yeah, quality, which is a really important point for us. Yes, true. Okay, so I think we will move ahead. And just the point here, which I think we've already said, is that, I think we can assist students a lot by encouraging them to talk about their thought processes. And I do believe we can encourage them to, that there is more than one way. And even if a student does come up with their favorite way, that they still understand that there's different ways to solve problems. And I did just put the vector problem. I'm not going to go through this, but I did put my way to do the vector problem. And I actually did sort of a combo, because my first step was a sort of canceling thing. And then the next few slides, which you guys will have after Sandy posts it, would be Lisa's proportion method for the vector problem at the beginning, and then Rodney's very elegant single equation answer. And we get the same answer, so we agree on the answer. And Rodney, do you want to add anything to that before?
No, I just noted it took 3 fancy ones to do that. And understand, if I'm doing a metric to metric thing, I'm a slide the decimal point person just as much as anybody else. I'm not married to this as the only way to approach a problem like this. So again, having a variety of tools and knowing which one's the most effective or efficient or something like that in a given situation, it is a good thing, I think.
Yeah. Okay. So where does this take us? So I think, the really key point here is that, we're pretty convinced that by putting a lot of this instruction into our little 1-credit class, in other words, by doing it consciously and taking the time to do it, we do think that students can succeed. And the problem is not that they can't do math. So, and Rodney, these are your words here.
Sure. Trust me, I'm very aware of the problem with a student that comes in, even to my math class, that's been damaged by past experience with math classes. And believe me, if you come in with the mindset of, I can't do math, you can't do math. Building a little confidence, stuff like that is something that's important. I often describe students with very little threshold for distinguishing between trivial math and impossible math. Math is either trivial, which translation I can do it in 10 seconds without a lot of work, or it's impossible. Translation, I can't do it within 10 seconds in a lot of work. And getting students to build on where they're at and be a little bit better than they were the day before or something like that is one of my initial challenges often with folks that have had some bad experiences in math world.
Yep, good. And I think we need to spend time with students on our own common problems like, conversions and solution making, standard curves, interpreting data, maybe statistical control charts, because that's, in some areas, that might be something you would spend time on, maybe preparing reaction mixtures, because that could be real important in molecular biology. So I do think that just time is part of the issue here. And developing, helping students to develop their own individual strategies. And, with more complex problems like the vector problem, we would do that in a molecular biology class, not probably in our first semester class. But the point is that the math is still just multiplication and division, and our students can multiply and our students can divide. So their problem is just figuring out when to do it, and we can help them with these problems. Okay, so I'm going to kind of turn this over to Rodney, because I think he's much more in touch with what's happening, than I would be, or many of us would be, into what the math world is thinking about this. So Rodney, I'll advance slides when you tell me, but why don't you go ahead?
Sure.
So
Yeah, you can go ahead and get into some of this. I think these are some observations I think, Lisa, you may have made with respect to how traditional math stuff goes. We've required more and more math classes in the high school, and there's good and bad aspects to that, I'm sure. Another thing that's been very prevalent is the Algebra 2 requirement. And you can blame that on or credit that to lots of things, Common Core, et cetera. I'll tell you, Algebra 2 is a really easy thing to teach in general. I didn't say teach well. And it's a really common perception that is sort of the stepping stone to anything that's college level. Some schools are requiring either at the state level or something exit exams, and you have to reach a certain level of proficiency. Sometimes it's a 10th grade graduation test, a 12th grade, et cetera. Colleges have often required placement levels based on standardized exams or some things that they do in-house. And if you didn't meet those expectations for college readiness, you were, I'm going to say the word, doomed to remedial coursework in college, and with many issues with that. So all of those things were different approaches to I want people to be prepared with math tools to be successful in subsequent coursework and or beyond. But there were problems with that.
Okay.
One problem, I think, is the Algebra 2 standard that you've got there. Algebra 2 was often viewed, I think, by many folks as the skeleton key. Hey, if they complete that, they're prepared to move on to any option they might want to, whether it's elementary education, medicine, engineering. Algebra 2 leads to calculus ultimately. If you're not moving on to calculus, we can call into question the Algebra 2 track for a lot of folks. And if you look at all majors, I believe that numbers vary a little bit. Less than 25% of all college majors require some type of calculus thing. So is that skeleton key that gives you the ability to be anything you want if you grow up kind of stuff really opening doors, or is it becoming a barrier to successive programs?
And I saw a statistic, may or may not be right, that only about 5% of jobs require calculus. Now, I don't know if that's true or, accurate, but that's a really small number of people who need calculus for everybody being prepared for calculus. Yeah. Okay.
The next one.
Okay.
So Lisa asked me to share a little bit of the things that I think that have occurred in the mathematics community that address some of the issues that we bring up here. In Ohio, and it's not the only place, but I'm most familiar with that, of course, is a number of alternative pathways to the algebra to calculus track have been developed and implemented. And that's not just in the college level, but it's trickled down into the high school level. So it's interrupting that algebra to calculus track that kind of leads off with Algebra 2 back in your sophomore, junior, senior year in high school. And some of those pathways that have been developed here, there's a statistics and probability track, there's a quantitative reasoning track, there's a discrete math for computer science foundations. And by the way, the quantitative reasoning one was a pathway I was involved with involving a mathematical modeling and reasoning course. Not algebra intensive, but a lot of problem solving, a lot of activities-based stuff, a lot of using math to accomplish something in the real world. And then data science is a brand new one that's just in its second pilot year here in Ohio and stuff. So I've included a hyperlink there for more information on any of those. Some of those things I think are worthy of considering for what's most appropriate for the biotech community and the type of students that you folks are looking for.
Right. And I have no idea, if more of our students were coming through these pathways, maybe we wouldn't need our little one credit course. I don't know. I have no idea, how this would impact our students because they're still mostly coming through traditional coursework.
Right. Lisa mentioned, the testing and stuff is a barrier and things. And I think that's something that's changed dramatically. And it's so dynamic. It's changing so much. I really couldn't give you the penultimate hyperlink here to go figure out what all the different admission standards are. They're changing all the time, it seems. There's huge differences between public and private institutions, university versus college versus trade schools. And it's really important to distinguish if you're looking at a college like my past employer here, that it's an open admission institution. If you've got a GED or a high school diploma, you can come to Rhodes State College. Your placement into subsequent coursework, though, may be dependent upon some measures. And often they're multiple measures, not just traditional ACT scores and stuff. Sometimes it's high school GPA. Sometimes it's a variety of factors, but multiple measures for placement are something that is implemented at a lot of schools. And then lastly, what was my last? There we go. The remedial developmental thing, my colleagues in the math community are well aware of this, but I don't know all the people in the math community, and I don't know how well this is scattered around the world here. But there used to be lots and lots of pre-college level remedial developmental coursework required for folks coming in, placing low, before they could take their first college credit bearing course. It's a death sentence. It's a pipeline with no output. Students would get into this, they would be marginally successful, they would accrue debt, they would never get to that college credit bearing class 1, 2, 3 years into their 2-year degree program. That's going away. There have been lots of initiatives in the math community now, and I've got a good hyperlink there through AMATIC, the American Mathematical Association of 2-year colleges, for co-requisite courses and things. Getting folks into that first college credit bearing math course their first semester in. Studies have shown through a lot of different sources, Dana Center being one of them, and there's others, of course, that there's no clear correlation between that initial math placement and completion of degrees, completion of programs and things like that. So there've been lots of work there. In fact, the National Association for Developmental Education had to change their name to National Organization for Student Success because the developmental education thing has got such a negative connotation now. So lots of new stuff.
We did a little study of our students, a very small study with maybe 30 students max, but we also found there's no correlation between their scores on a math entrance exam and their actual success down the line. So anyway,
Here's a question for you, Lisa.
Yep, go ahead.
Beatrice Villar says she teaches upper genetics too, and has students after 2 years of math, chemistry, and science courses are still unable to do dilutions and ratios. And she's wondering, I guess, what's missing and how to prepare them to do this in a lab.
Okay, so I guess I'll give the same answer. Dilutions, ratios. Dilutions is a huge, big issue. It was another topic I thought about for today because it's so important and it's such a sticking point for our students. It is part of what we teach in our little one credit class. So I guess, yeah, it's in the book. I've got a slide with the book at the end. There's a ton of stuff about dilutions in that textbook. And Rodney knows because Rodney heroically, I think this was a really big deal, checked every single problem in that book to make sure the answers were right. And most of them were. I give myself credit, not all of them, but there's a lot of stuff about dilution. So does that kind of, Sandy, is that answering the question, or whoever asked the question, does that sort of answer it? I do think we just teach it directly in our class, and then we do it in our 1 credit course.
Beatrice, does that help? I used to just teach them exponents.
Exponents?
Had all the exponents.
For which, oh, you're talking about dilutions. Yeah, but you're teaching them, so, I mean, you're doing it with them. I mean, I guess I'm not expecting them to come in able to, I guess the answer to the question is that I don't expect them to be able to do that when they come into my class, even if they've had other classes, even if they've had math instructor, whatever. I teach it formally in our 1 little credit course is where we teach it.
Yeah, I mean, my question was more like a comment that I see, you know, I teach first level, second level, and I see how those skills are not really carry on, and really that there's something, maybe because the opportunity we give them in the labs to practice those skills, we give them everything so done all the time, right? So I wonder when we teach in a community college, we're moving, and I'm kind of worried about their skills. So still, I think there's something missing in there that we should be kind of insisting more in carrying those skills from class to class with some type of assignments on assessment.
Oh, okay, yeah. Yeah, and I guess that would be something that each program has to figure out how to put it into their system.
Right.
You know, like the way that we're doing it is not necessarily going to work for some other school where we put it in our classes.
Yeah, and I remember, you know, also talking about the idea of creating a 1 credit class on math, but you know, every college has its own opinions about that, and just adding one more thing in there, right? So
that's true,
and
and totally get that. And we did have to take something away. And the other thing I just want to mention is that we took the word math out of the course description and the course title. We call it calculations. And once we took the word math out, we got much less resistance because we don't call it a math course. Therefore, the math people don't feel like we've done something they should be doing.
One quick comment in the chat. There's a tremendous amount of good stuff coming up in the chat. I wish we had time to address it all. But Bob, you made the comment about in California, the students being placed in the transfer math. If they lack remedial skills and knowledge and stuff, then the co-requisite options to go with those transfer courses will help with some of the issues that you're bringing up there, I think. So just to let you follow up on that.
Okay, so I'm next.
Oh, sorry.
Okay,
Matt had
just
a comment too.
Okay, go ahead. Yeah. Do you want to say what it is, Sandy?
Sure, I'll just say it. He said the opportunity to practice and gain confidence, both on paper and doing the dilutions in lab, is lacking in typical bio lab classes, which is a problem. Biotech classes, though, you do a lot of it. And I used to teach a lot of math. I mean, a lot of it in our media and solution preparation courses, and in our biotech courses, I had math like all the way through.
Yeah, and that's a really good point. I do believe in teaching in context, and you know, with some students that works really great. The thing that I discovered when I started with sort of very beginning students was that if I tried to do those kind of calculations right in my class, right when we were trying to make the solution or trying to make the reagent or trying to do the 1 molar solution, it was just consuming all the time in my class. So instead of making the solution, we were doing the math on the board, and then my 2 hours was up. And so that's one of the reasons why we went to this separate math class, so that we could work on that outside. But I think if your students are ready and you can do it within the context of your class, that's great too. So, you know, again, there's going to be different solutions to these problems in different places.
And you have 4 minutes.
Oh no!
And Matt has his hand up.
Oh no, we only have 4 minutes, but we have to have.
I'll make it quick.
Okay. Okay.
To your point about not being able to do in the class, I experienced the same thing. So I made it like a pre-class exercise where they work through a handout and then we'd come and give it a try. So little tricks like that can be good. And also like building drill things like low stakes things into Canvas or whatever your course delivery system is, where they can try things repeatedly without being penalized, kind of helps build some of that confidence. But it really, my first comment really was, those fundamental freshman, sophomore lab classes aren't really designed to show you how to do lab work. It's illustrating concepts for the lecture.
That's right.
And so if we are expecting students to come out of those lab classes with those sort of skills, it's not really what they were experiencing. So that's just been my experience here.
Yeah.
And why a lot of students who take biotech and then take some of the chemistry, later chemistry, are being much more successful in them.
Yeah, I'll bet that's true. Okay.
Thank you.
And yeah, and thanks for those comments. They're all great comments. Michael Hacker, are you here? Michael? Because if
I
you
don't
are,
think so.
Michael's not here.
There he is.
Oh, I guess
Okay.
he is.
And the reason why I wanted to bring Michael in at this point, we only have a couple minutes, right, Sandy? We're
Mhm.
kind of, okay. Michael is involved with, he's the PI for the needed math project. And he might have some ways that if people want to get involved, that they can get involved with this ongoing math project. So Michael, you want to say a couple things to us?
Sure. Are you hearing me okay?
Yep.
Great.
I'm hearing
Okay.
you.
Thanks. Hi, folks. Well, first, thanks, Rod, for reminding me to go out and pull out the stakes in my backyard that we put in to scare off the pica moles. Actually, they're mega moles in my backyard.
Mhm.
Very good.
So, folks, Lisa and Rod and I worked together on a needed math conference a couple of years ago, where we brought together industry people, math people, and technical program faculty in 3 domains: manufacturing, IT, and biotech, to have some dialogue about the math that's needed in those domains. Our current project is an outgrowth of that conference. It's an ATE research project, and the focus is on aligning what's taught in community college math courses with what manufacturing technicians actually need to be successful on the job. We're putting the finishing touches on, and I'll be quick, a 40-item survey that we intend to send out to 5,000 manufacturing technicians, manufacturing technical and community college faculty, and applied mathematics instructors to compare their perceptions about the mathematics that's needed. And so we're about ready to pilot test the survey. We need to validate it. Taking the pilot survey shouldn't take any more than 20 to 30 minutes. We would be very grateful for your time and your expertise in helping with the pilot test. We're attempting to survey people who work in a range or teach in a range of manufacturing sectors, like materials fabrication, food manufacturing, and we're anxious to get the biotech community's perspective. So once we finalize the Qualtrics version of the pilot, might you folks be willing to pilot test the survey? We have 2
Okay.
variations. One is for technical educators, and one is for the industrialists, technicians. And so, can we ask for your help in pilot testing it and sending the link to the survey to a colleague or 2? We'd have it ready by the time of the ATE conference. We'd need it back by mid-November.
I
So
can send
that's
it
my
out to you.
plea.
Okay, that's great. So
Yeah.
Sandy, can you work with Michael to get
Yes.
sort of this? Great. So Michael and Sandy will work to get this. So, and if people want to get involved and down the line, maybe with some other things that the Needed Math Project is doing, that would be great. So I'm just gonna
Thank you.
say that, thanks, Michael. There is a slide which has some references to projects that identify needed math. There's a reference here on the final slide, to this book. That was the book we put together for our class, for our little math class. And the final thing is, in 1953, you told me I would need that polynomials would come in handy someday. How much longer do I have to wait? And that's our last slide. I love this cartoon. So at this point, Sandy, I think we're out of time, but I think we can stay on, right? And if people wanted to chat, because I know that there is some discussion, and I'm not seeing the chat, but if people wanted to, so those of you I know who have to go and teach classes or whatever, certainly would do that. And then Rodney, you can stay a little bit too, right?
Sure. If they turn the
Okay.
recording off, we can really get down to some serious
I'll
answers.
turn it off. Okay. But
Okay.
before I do that, I do want
Oh
to.
yeah, your survey.
Yeah, I'll stop the recording.